In this section, we're going to be going over mass spectrometry. This is one of the techniques we use to figure out structures of molecules. In the case of an unknown, it provides the form of mass, but even when we know what the structure of the molecule is, we'd still like to run mass spectrometry on the sample because it tells us primarily what the form of mass is. So that is definitely what the primary use is of mass spectrometry, is to determine that form of mass of a compound. When combined with a gas chromatograph, which mass spectrometers often are, because really what you want to hit the mass spectrometer at any given time is a pure sample. So if you have a mixture of samples, the gas chromatograph part of it is separating the mixture into the various components, and then each component in turn enters into the mass spectrometer, and we get the form of mass of each component. Okay. Sometimes these are paired with high-performance liquid chromatography, HPLC for short. I've got a couple of these in the Shasta College laboratory as well. We're not using them right now, but that's similar to gas chromatography, except that we're using a liquid phase instead of a gas phase. So, but the point is the same, is to separate components of a mixture. So, all right, so mass spectrometry is both used to identify and quantify compounds in a mixture. So we use this for both purposes. And qualitatively speaking, in addition to the form of mass, sometimes we can figure out structural properties of the organic compound. So if we have a mixture of two isomers, sometimes we can figure out which of the two isomers we're dealing with. So that's sort of the qualitative aspect of mass spectrometry. For us, though, what we're looking for is the form mass of an unknown structure is what we're looking for. Now, our Shasta College mass spectrometer, we own a GCMS system. I've probably already explained that we got it as a donation from the crime lab in town. And it's old enough that it was still manufactured by Hewlett-Packard, which used to have an instruments division some time ago. Now Agilent is the company that bought out the HP Instruments division. So it's not labeled Agilent, but Agilent runs the show now. We also own two LCMS systems. So that's the liquid chromatography systems. They're not operational yet. One is pretty close to being operational. That's the Agilent system. And we got that Agilent system, by the way, from a crime lab, but this time in San Francisco is where that one came from. The water system came from a pharmaceutical company way down south in San Diego. And that's a much bigger mass spectrometer. That one can handle form of masses higher than 500 atomic mass units. So it's capable of looking at peptides and small proteins, I believe. GCMS primarily used for volatile mixtures. So when we have a mixture of volatile components, meaning like relatively low boiling points, they're easily vaporized, we can use GCMS. In fact, we've been using it all last semester and fall semester for our mixtures. LCMS used more frequently for polar compounds, ones that have higher boiling points, or they have to be dissolved in a polar solvent. And a lot of the times you're going to find a pharmaceutical company owns many of these LCMSs because they're using it all the time to look at purity of compounds. And, you know, just like we use it, they're going to prove that they synthesize the structure that they say they did. Okay, so that's the use. Now, we're going to go over a little bit of instrument theory. I don't want to dwell too long on this, but the way a mass spectrometer works, at least they used to work this way. I think the more modern systems don't use this method. The more modern systems are called quadrupole analyzers. So it works a little bit different in this section here, but they both, all instruments have to ionize a sample. So I've got this molecule that I want to figure out the form mass for. It doesn't matter really if it's a liquid. We can get away with solids sometimes, but it enters into the mass spectrometer, and the first thing that happens is you have to figure out a way to ionize that molecule. Remember, ionization means, you know, create a charge on it. Now, typically what we're doing is creating a positive charge. That's primarily what happens. And the way you create a positive charge is by knocking loose an electron from the molecule. Pretty much the way we do it, I mean, this is the way we do it, is we bombard the sample. Our mass spectrometer bombards the sample with electrons, high energy ones. And the hope is that one of these high energy electrons hits our molecule and displaces an electron and creates a positive charge. And with that positive charge on the molecule here, we can cause that positively charged species to accelerate down this flight tube right here. And once it's ionized, we can't do this until it's ionized. It's got to have a charge of some kind. And then it enters in this curve. I call this deadbands curve, because similar to a big truck on an icy road, a big truck is going to have a hard time making this turn on an icy road, and it's going to tend to crash into the walls here. Likewise, a super light car is going to make this turn too easily because it's light and it's going to crash into the walls here. So only that molecule or particle or ion that has just the right mass given an electromagnetic field is going to make it through, make the turn, and make it all the way to the detector, okay? So only molecules or ions with the right form of mass is going to make it through at any given time. And the right mass to make it through depends on the strength of the magnetic field. So we can continuously vary the magnetic field strength to allow other types of molecules to make it through at any given time. So really what you have to do is you have to do a sweep. You have to sample different magnetic strengths, and eventually you're going to get molecules to get through of all kinds of different masses. Okay, and the detector's looking at this at all times. It's seeing what comes out on the other side. This little part of this diagram is meant to represent a vacuum, so we always have to have a high vacuum pump attached to the mass spectrometer. For obvious reasons, we don't want our ions to be bumping into air particles, so that would be bad. So this has to be completely a vacuum. And in fact, if you look at our mass spectrometer, there's a gauge up there. It reads the pressure in torr, and it's really low torr reading, okay? And that runs all the time. We always have that on. The detectors here, the detector these days are hooked to computers, and the computers generate a mass spectrum. This is a typical mass spectrum. Now keep in mind there's a lot of... Oops, let me back up here. That was an accident. Keep in mind there's a lot of lines here, but these are one molecule. We're going to talk about why you don't see just one line for one form of mass. We see all kinds of different lines, and that's because the molecule, with all this high energy ionization going on, tends to break down into smaller pieces, and these are the pieces that it fragments into. MZ, that's the symbol for mass to charge ratio. That's truly what you measure in a mass spectrometer. And so down here is something like 0. Over here is whatever. It's 500 atomic mass units, whatever it is for the mass spectrometer. And then this is abundance. So you'll typically see y-axis is abundance. Sometimes it's absolute abundance. In fact, our mass spectrometer is absolute abundance. And sometimes you see relative abundance, where the biggest peak, which is this one in this case, is just arbitrarily set to 100%. Okay, so that's relative. This peak right here, I'll probably mention this terminology a couple times as I go, but this peak right here that I'm pointing at, hopefully you can see that, the one that's the rightmost peak is typically called the parent peak. So that's going to be the molecular mass or the form of mass of the compound that you actually put in there. So, if it's acetone, then this should be acetone's form of mass right here. The tallest peak, or the most intense peak, is called the base peak. Okay, so you'll hear these terms all the time in mass spectrometry. The base peak is the largest peak, and the parent peak is usually the rightmost peak, or sometimes it's called the molecular ion peak. That's the same thing as the parent peak. Okay, now that's how these older mass spectrometers work. Is they use these magnetic fields like this. Okay, like I said earlier, the more modern approach is to use a quadrupole, but the idea is the same. So you're just filtering different masses of molecules through it. It just works a little bit differently. And these newer instruments are much smaller too. The older mass spectrometers used to take up, rumor has it that Shasta College used to own one, and it took up half a warehouse or something like that. Some ridiculous rumor about that, but they were much bigger back in the good old days. Now, I mentioned that ionization is a key step when it comes to mass spectrometry. So the molecule has to be ionized somehow once you put it into the instrument. And one of the common ways to ionize a molecule is called electron ionization, EI for short. You bombard the molecule with high energy electrons to knock loose one electron from the molecule. So you hit it with electrons, and hopefully you dislodge an electron from the molecule. You create a positive charge. And our GCMS uses this type of ionization. In fact, when I set up a run, you create what are known as methods, and in the method I can set the voltage or the energy of impact. And some molecules are really fragile, so I have to reduce the voltage, and in other molecules it takes a lot of voltage to get them to go. So that can be tailored to your molecule. Other methods of significance, there's all kinds of methods for doing this. Electrospray ionization. There's chemical ionization, so that's some chemistry happening to ionize the compound. Atmospheric pressure chemical ionization, APCI for short. This is the type that I remember from the pharmaceutical industry. We had this type. And matrix-assisted laser desorption ionization, MALDI for short. There's a mouthful. That one's kind of a fancy pants one. I think only really research laboratories are using that type. Maybe pharmaceutical companies. I'm not sure. But anyways, all kinds of different ways to ionize. Ours uses this first type. It's called electron ionization. We hit the molecule with electrons. We hope to dislodge one electron, create a positive one charge. Okay, we have to have a positive charge. Now, here we go. So this is the first step. We're still talking about ionization here. So we've just loaded, well, we wouldn't do this for real, but here's methane. Methane's a gas. It'd be really hard to do this. But methane, we hit it with whoop, I keep doing that. I apologize. Let me back up. We hit methane with a high energy electron. It smashes into this methane molecule. And the hope is that this electron knocks loose one of these electrons, making this bond right here. And what we end up with is a very strange species where this hydrogen is still technically attached to this carbon, and yet it's only held together with one electron, and that creates a positive charge. So you'll see this symbol right here where it's a positive charge and one electron, and it's just barely holding this thing together. And notice that there's now two electrons because we initially had the first electron and that dislodged another electron, so now there's two electrons that are produced. Okay, so once we have that positive charge, now we can cause this ion to accelerate down the flight tube, and it's going to go around that dead man's curve like we talked about, and we're going to analyze this. Okay, so that's called ionization. That's what we're doing in the first phase of this process. Unfortunately, well, not unfortunately, I guess it's just kind of, it's one of these things that happens. Not only do you get the molecular ion forming, that's what we really want because that's going to tell us the form mass of the compound. But the other thing that happens is when you're hitting a molecule, say like ethane with high energy electrons, not only do you get the molecular ion species, and here's the molecular ion species, here's that weird sort of association with this carbon and this hydrogen, it's barely held together. The mass to charge ratio, or the atomic mass of this, is 30 atomic mass units. And that's pretty much the complete molecule. Remember, electrons weigh 1/10,000th the mass of a proton or a neutron. So losing an electron really doesn't affect the atomic mass at all. So it's still 30, even though we lost an electron. So 30. But what happens some of the time is, it does happen, is that instead of doing, instead of creating this molecular ion species, you simply knock loose a hydrogen radical, and you've got a carbocation. And because this has a charge like this, it's still accelerated down the flight tube, and we're still going to see it on the detector. And this one is actually 29 atomic mass units because we lost a hydrogen. What else can happen? We can have complete fragmentation of the molecule. So it breaks in half. One half produces a carbocation, the other half becomes a radical, and the carbocation here has an atomic mass of 25 atomic mass units. This radical right here, we don't care about the atomic mass because it's not accelerated. It doesn't have a charge, so there's no point in looking at this because it doesn't accelerate down the tube, so it just flies out the waste, I suppose. There's like an exhaust port. In every case, what ends up happening is we produce two electrons. So no matter whether we're talking about this, or this, two electrons. We hit it with one electron, we dislodge an electron, we either get this molecular ion, or we get a carbocation, or we get these two species and knock loose two electrons. In general, this is still a very simple molecule in ethane, but in general, when it comes to predicting what the base peak is, it's really hard to do sometimes. But when you're looking at carbocations, the same rules apply as always. You're looking for the most stable carbocation. So, of course, that's going to be the tertiary carbocation or the allylic or the benzylic. Tertiary is more stable than secondary. Secondary is more stable than primary. So something like this primary carbocation is pretty difficult to produce, as it turns out. Actually, this is a methyl carbocation. This is the worst carbocation. This one is a primary carbocation, so we would expect this one to be in greater abundance than this methyl one. Okay, so we're hoping for just a little bit of this one, though, because this is the molecular ion species. This is the atomic mass of the overall molecule. But that's what happens when you have bigger and bigger molecules. They fragment, they produce a lot of pieces, and all these little pieces, as long as they have a positive charge, they're going to show up in the final mass spectrum, and that's why we see a complex pattern. Even for one molecule, one pure molecule, we see all kinds of peaks, and those are the fragments. After ionization, we've got acceleration and deflection, so those ions that we created in the first step are accelerated down a flight tube. I showed you the schematic earlier. And that's pretty easy to do. As long as we have a positive charge on the molecule, you can accelerate these things. And eventually, as we talked about before, they're going to hit that curve, dead man's curve, which is the magnet. And depending on the exact magnetic field strength, Only certain masses are going to get through that curve at any given moment, and that's why it's totally necessary to sweep through different magnetic field strengths to get or to make sure that all masses make it through eventually. Okay, so after we accelerate and get through the curve, these particles, these ions, are going to be heading towards a detector. Okay, that's essentially how we separate the masses. Now, the detector itself, we haven't spent too much time talking about this so far, so it's essentially a metal surface. I'm going to go ahead and try to draw this. I'm not a very good artist here, but we'll do our best. So the metal surface, picture something like, you know, a metal. And the metal, we'll just call this metal. The metal is just a metal surface, and it's hooked to a power source of some kind. I'm going to draw a crude battery here. This is a battery. Okay, with its little posts and that kind of stuff. I should have hooked the wires to the post. And then this is hooked to a computer of some kind. Here's my ancient computer with a little keyboard off to the side here. And there's a screen, of course, and we're going to, you know, plot some stuff. And the computer's got a keyboard and all this kind of stuff. And eventually we're completing this circuit here. So this is a full circuit. We've got a power supply. We've got a way to monitor what's happening in the current. Okay, so as these positively charged species make it through the dead man's curve, we'll just call this S for species with a positive charge. These things hit this metal surface eventually, and what happens at that point is an electron from the metal itself is given to the positively charged species, and that creates somewhat of a hole in the metal because it's lost its electron to the compound. This compound eventually gets sucked out of the chamber. Now, as soon as that electron is lost, there's a power supply that's providing more electrons. And so really what we get at that point is as soon as we lose this, we get a current flow, okay? And that current flow is something we can actually quantify on the computer, and that's essentially what we're measuring is current. But current is proportional to the number of positively charged species that are hitting the metal surface. So more of these positively charged species with this mass hit this, the greater the current, and we register that on the computer, okay? Now, of course, with different masses are going to give rise to different currents, and that's why we see various peaks in a mass spectrum. We're going to see the parent peak, we're going to see the base peak, we're going to see all the masses, the fragments hitting this detector at any given time. Okay, but that's the essence of how this detector works. All right, so let's carry on here. So let's take a look at what else we can do. The mass spectrum itself, it's pretty simple to create. It's got the two axes. On the x-axis, we've got the MZ ratio, that's the mass to charge ratio, and that's essentially the form of mass. And then on the y-axis, we have abundance. So I just got done saying that the number of positively charged species that hit the detector creates a current, and that's really, you know, abundance is what the y-axis is, okay? All right, so even pure samples typically show a complex mass spectrum, so there's not just one peak for one molecule. Remember, we hit this molecule with high energy electrons, and so that tends to cause the molecule to break down into smaller pieces. So it's not just one parent peak, we see all kinds of peaks, and those are due to the various fragments that are making it through. The rightmost peak, we've already described this. The terminology is, it's called the parent peak, and that's the one we're after because that's going to tell us what the form of mass of the compound is. And we always have a base peak too. The base peak is, of course, the most abundant peak wherever it's at. Okay, really what that's saying is the base peak is the most stable carbocation is what that's going to be, the most abundant. All right, so here's a typical mass spectrum. I actually generated this mass spectrum I actually did this on our instrument, and so we've got this molecule right here. This is 2-pentanone, and I'm going to do a fast check. What I'm going to do quickly on the side here, I've got my calculator. I'm going to calculate the form mass of this just to make sure that this is right. I have a feeling the structure's wrong, but let's check it. So 5 total carbons times 12.01 plus 16 for the oxygen, and then plus 3, 5, 7, 10. And that gives me a formula mass for this of approximately 86. Actually, I think this mass spectrum is right. So here's the parent peak. So I'm going to label this. The parent peak, again, is the rightmost peak. And that's really the most interesting one because that's going to give us the formula mass of the compound, and that matches up perfectly. If this is 80, 82, 84, 86, here's that big peak right here, parent peak. Okay. This one being the most abundant, of course, is the base peak. Off the top of my head, I can't really tell you which fragment is producing that base peak, but it's, some smaller version of this molecule that's producing the most stable carbocation. That's going to be the base peak right here, and then a bunch of other peaks for other fragments. Probably what you're wondering right now is, well, this is the rightmost peak, and so why isn't that the parent peak? I mean, you could call that the parent peak too. And so why is this so much smaller than this one? In fact, for carbon-containing molecules, you're pretty much going to see this pattern where you see this tiny little peak right here and a much larger peak to the left of it, which is 1 atomic mass unit lighter than this smaller one. So what does this do to? What's this smaller one? Well, most of an organic molecule contains the isotope carbon-12. So that's the predominant type of carbon isotope, carbon-12. That's about 99% of a given molecule. The other isotope is carbon-13, and that's roughly 1%. And remember, carbon-13 is 1 atomic mass unit heavier than carbon-12, and hence we do see this smaller peak. I suppose I think I can see a tinier peak right there, and maybe there's a chance that, our molecule with 5 carbons, maybe there is a chance that it has 2 carbon-13s, okay? So that would be 2 atomic mass units. I don't know what the isotopes of oxygen are, but that could be also influencing the height of this peak as well. So there's some oxygen isotopes as well. So those are isotopes is what we're seeing. In fact, this is one of the principal ways that people figure out the ratios of isotopes in a given sample. Now, eventually we're going to see halogens. Halogens are really interesting in mass spectrometry because something like bromine has 2 equally abundant isotopes, and we see this. We're going to see an example of this in just a second, but it's got 2 equally height peaks, which is really cool. Okay, so let's move on. In fact, here it is. Here's the halogen discussion. So halogens are really easy to spot. In fact, the first laboratory experiment that we're going to do is I'm going to issue you some unknowns, and I think all of them, or the vast majority at the very least, contain a halogen, at least one halogen, and only one halogen. And they're really easy to spot because if your molecule, your unknown, contains bromine, what you're always going to see is the parent peak has 2 equally heighted, I don't know if that's a word, but I just made it up, 2 equally heighted peaks that are spaced 2 atomic mass units apart. So let me just kind of sketch out here for a second the 2 common isotopes of bromine. One isotope that's fairly common, it's about 50%, is bromine 79. The other one that's common is bromine 81. That's about 50% as well. And remember, when you look up at the periodic table, you see the average isotopic mass. And that's why bromine, when you look at it, is approximately 80 and not 79 and not 81. So 50-50, these two, it averages to about 80. And nonetheless, or that's the reason why we see this pattern in a mass spectrum. So bromine, really easy to spot. Same goes for chlorine, although it's a little bit harder to spot chlorine. This looks a lot like carbon, except that the second peak is spaced 2 atomic mass units from the first peak, and that's the difference between carbon, because carbon's spaced 1 atomic mass unit, and this peak is much smaller compared to this peak, so the ratio of these two is much more closely related. So I think off the top of my head, I want to say one of the chlorine species is chlorine 35, and I think the other one is chlorine 37, and this is not a 50-50 ratio. This is more like, I want to say thirds. I want to say, let's see, I think the average is 35.45, so that tells me I think this one's roughly, and I mean roughly 66%, and this one's roughly 33%, something like that. Okay, and that's why we see this pattern right here. We're not going to have any unknowns that have 2 bromines or chlorines or 3 or whatever, but you could still look for those patterns too, and that's what you're going to see in patterns. So this is halogens. And so the unknown set that I'm going to issue in laboratory, that's why I choose those, is because they all have halogens, and they're really cool when you look at them in mass spectrometry. Okay, so halogens are very easy to spot. Okay, so let's move on now. So here is a real mass spectrum of a chlorine-containing molecule, and let me just kind of point out that the parent peak, once again, is way down here. It's the rightmost peak, so parent. And I've already kind of spoiled the answer to this, but this is a chlorine-containing molecule, and I can spot that because here's the first one, which is larger than the second one, and these 2 peaks are spaced 2 atomic mass units apart, and that's characteristic of chlorine. I suspect too, maybe, I'm not going to do the math here, but when you look at the parent peak and then the next peak down here, I'll bet you that those are approximately 35 to 37 atomic mass units spread apart, and that's loss of chlorine. So here's the parent peak, but maybe with all that energy happening at the first phase of mass spectrometry, you knock loose a chlorine. That's the gap that we're looking at. Is it 35? Yeah, it looks about 35, and that's a loss of a chlorine between these two. Okay, so that's a chlorine-containing molecule. Let's now look at something else. I think we have a bromine-containing molecule next, and that's exactly what this is. So here's a bromine-containing molecule. Again, this was run on our mass spectrometer. Here's the parent peak. Again, I'm going to mark this. Parent. Of course, this is going to be the base peak. That's the most abundant. And the parent peak contains bromine. I can tell that because these two peaks are spaced 2 atomic mass units apart, and they're approximately the same height, which means that, you know, it's bromine. I mean, we're talking about bromine 79, bromine 81. Now, looking at this base peak, does this fragment still contain bromine? The answer is yes, actually, because these two peaks are still the same height. That means that whatever this base peak is, we've not lost bromine at this point. We lost something else, and there's still bromine present. Same goes for this one right here. We still have bromine present. And then notice that the large gap between here and, say, this other series of peaks. And bromine, again, is about 80. So that makes sense that this is loss of bromine, this gap right here. Let's just kind of mark this right here. This gap right here, that's going to be, if you look at it really closely, you can do that on your own time, but I'll bet you it's about 80 atomic mass units difference. Okay, and that's loss of bromine. All right, so parent peak, base peak, and this one also contains bromine, and then this gap is 80 atomic mass units. All right, so let's see. Let's talk about fragmentation again. Even pure compounds give rise to complex mass spectra due to fragmentation patterns. So it's not just the parent peak that we see the smaller fragments. And sometimes we can use these fragments to help identify unknown organic compounds. Sometimes, you know, and I do mean sometimes. Other times it's not so useful. I think when it comes to our unknown determinations, I don't think we're going to really look too closely at the fragments and the patterns. I think NMR spectroscopy is going to be much more important for that. So we're really going to use it for form of mass. But let me just mention a few things about fragments. You know, when you look at the mass spectrum, you frequently see gaps of 15. And when you see a gap of 15 between two peaks, that means that we lost a methyl group. So if you think about that, it's carbon with 12 atomic mass units plus 3 more for the hydrogens. Another situation, you lose 29. Well, guess what? That's loss of an ethyl group. So when the molecule breaks down, it tends to, have gaps in the mass spectrum of, 15, 29, et cetera, and that's due to loss of alkyl groups. Now, there are a lot of complex loss patterns in mass spectrometry. I just don't think it's worthwhile to learn all these things. Even some of them have names like the McLafferty rearrangement. If you're really interested in this, you can read about it in the textbook. I'm sure the lab textbook has a discussion of this as well. Pavie is really good about talking about mass spectrometry. I even have an advanced organic chemistry structural analysis textbook that you can look at that really talks about these complex loss patterns. But I don't think we're going to spend too much time other than mentioning just a few little details. All right, so I'm also going to mention at this point that there's a very useful website out there. I use this all the time for lecture. I use it for the laboratory. Let me just start this movie here real quick. So the way you find it is just go to Google, type in Japanese spectral database, okay, and the top hit, as you see, is going to be the right link. This is a website coming out of Japan. You need to scroll down a little bit, agree to the disclaimer, and then you're going to see a search box eventually here. And what you're going to do is you're going to put in the compound name, or you can put in a molecular formula, or you can put it in a range of molecular weight. The CAS registry number is a number that every compound has. And if it finds your compound, what it's going to do is it's going to come up with all molecules that fit that name. And we're just looking for acetone in this case. We want to look at the infrared spectrum. Infrared, we're going to get to eventually. You can bring up the mass spectrum. I'm not sure if I'm going to do that in this video, but let's see if I do. Yes, I do. So here's the mass spectrum, and you can see that for acetone. And anything else really that you want, carbon-13 NMR, hydrogen NMR, mass spectrometry, infrared, all these things are usually typically given at this website. So very useful. I would highly suggest that you bookmark this website at some point. Okay, very useful, especially for the lab. Okay, so I'm going to take you as the last part of this little chapter or this section. I'm going to take you through some practice problems. So I'm going to take you through some sapling learning problems that you're going to get a chance to do these over again once we get to class. Really this semester, the plan is to open up these assignments only during class time, so I get a chance to work with you through these problems. But here's a sampling of the problems that you're about to see in the coming week. So let me turn on my pencil here. So given the parent compound, draw the mass spectrum fragment that is observed at a mass to charge ratio of 71, including any hydrogen atoms and the charge. Okay, so the first thing that I'm probably tempted to do is, since this is the overall molecule, what I want to do first is calculate the form mass of this. 1, 2, 3, 4, 5, 6, 7 carbon atoms. So 7 times 12.01. And then plus, how many hydrogen atoms do we have with 7 plus 2 more? 16. So I'm getting a form of mass, let me just write this in here, a form of mass of 100.1 atomic mass units, or grams per mole, however you want to look at that. And that's for this molecule, but we're looking for what the fragment is. So in other words, you run a mass spectrum of this molecule, and the parent peak is going to be 100 atomic mass units, but what about this peak that we saw at 71s? And that's going to be a smaller version of this molecule. So let's do this. We're going to take 100.1 minus 71 and see what we get. And so really what we lost from this molecule is 29 atomic mass units. And right away, I just got done telling you this. With loss of 29, that's telling me that it's probably an ethyl group. So we lost 2 carbons at 24, plus 5 hydrogens is 29 atomic mass units. So really what we're going to draw as our answer is 1, 2, 3, 4, 5. And we just got to be a little bit careful about how many hydrogens we attach to this end carbon. All these hydrogens or carbons are here. This carbon's here. But how many hydrogens should be attached to this carbocation? I suspect only 2. You know, that's how we get the carbocation. But let's just double check that. So we've got now 5 carbons. And then plus 3, 5, 7, 9, and then 11, I think. And that's what it is. So this carbocation species right here, this fragment, has got a mass to charge ratio of 71.1. Okay, so that's the answer. That's what they're looking for. We saw this in the mass spectrum, 71 atomic mass units. It's going to be due to this fragment. So this is a fragment that was generated from this overall molecule once it fragmented. Okay, so let's see what other trouble we can get into in this homework assignment. So here's another problem that I lifted from sapling learning, obviously. So here's a pretty typical mass spectrum. We've got the parent peak at 100. The mass to charge ratio is listed on the x-axis. The relative abundance is on the y-axis. Our mass spectrometer, keep in mind, doesn't do relative. It does absolute. So what is the molecular form of this alkane? Now, this is something you're really going to have to get good at in terms of our interpretation of mass spectra. In fact, it's going to be more than this. We're going to have some other spectra too, but really you need to figure this out quickly. So the parent peak, of course, is going to be the rightmost peak. So this is the parent, and that's the interesting one. In fact, really the base peak isn't going to be so useful to us. It's the parent peak. So parent peak 100. I don't know if there's really a good method out there for figuring out what this chemical formula should be, but the good news is there's only carbon and hydrogen. We don't have to worry about oxygen and nitrogen, all this other funky stuff. So I'm just going to take a guess. I think there's probably 7 carbons in this. So what I'm going to do is I'm going to assume 7 carbons times 12 is 84, and then that means so 84 due to the carbons, and that means there must be 16 hydrogens to get to 100. So I swear I just guessed at this, but I happened to guess correctly. So C7H16 is the chemical formula, and I assure you that when you do the form of mass calculation for this, it equals 100. Okay, so that was a good guess on my part. I guessed 7 carbons, and then I figured out the rest. Okay, it wasn't too challenging. Now, eventually, we're going to have more challenging problems. You're going to have real spectra, And I'm going to come up with, I have a handout that I created years ago that you can work through. It's not only looking at the mass spectrum, but we also look at carbon NMR. So there's some other tricks that we can pull to figure out how many carbons there are, how many hydrogens, how many oxygens, that kind of stuff. I will say, though, another little hint, as long as I'm here, is typically when you see a mass spectrum, and in the situation that you see the parent peak has an odd mass number, that's usually a sign that there's one nitrogen, or at the very least, there's an odd number of nitrogens. So nitrogen, when you have an odd number of them, gives rise to an odd form of mass. Okay, if it's even though, that's less helpful. We don't know what's going on. It could be oxygen, could be carbon, but odd mass numbers means odd number of hydrogen. Excuse me, nitrogen. Okay, so let's see. I think this is the last sample problem that I have. Select the compound that was used to generate the mass spectrum. This one's even easier than the previous two because we have possible choices here. In fact, this is really easy because I think we already solved this. I'm almost sorry that I put this one up here. We just saw a second ago that this mass spectrum, let me just verify that to myself. So 171. Oh, it is different. Okay, I take that back. It is different. All right, so we've got a couple different compounds here, and we're asked to identify which of these compounds is this mass spectrum. And what we're going to do is, considering that this is the parent peak, it is, I already know that this 100 atomic mass units is associated with C7H16. We proved that in the previous problem, so I can immediately eliminate hexane. Doesn't have enough carbons, so heptane's okay. This one has too many carbons, so if we have 2-methylheptane, it's got 8 carbons, that's no good. And I think it's really down to these two. I think this one has 7, and this one has 7 as well. And so heptane versus 2,4-dimethylpentane, that's really our choice. I suspect that the answer is heptane as our choice, because when I look at this gap right here, 171, that's a difference of 29, and that's pretty much loss of an ethyl group. So 1, 2, 3, 4, 5, 6, 7. Really, I think what you're going to see is loss of this guy right here versus this other compound. You know, that makes sense in terms of this gap. It's loss of 29 atomic mass units. Versus the other possibility, which is 1, 2, 3, 4, 5. I think the most likely loss of carbon on this is going to be a methyl group, or this methyl group right here. And that's going to be loss of 15 rather than loss of 29. And the reason I suspect that this is the common loss of carbon is because the carbocation that's produced is going to be a secondary carbocation rather than in heptane's case, which is primary. So I don't think you're going to see, I don't think you're going to see loss of 29. I think you're going to see loss of 15, and that's my suspicion. So I think the answer is heptane, just based on the fact that 100 minus 71 is 29. I suspect that it's an ethyl group that's lost rather than a methyl group. Okay, I think that's the last problem. Let me just kind of double check here for a second, but I think that's it for this chapter. We were looking at mass spectrometry. We looked at the various phases of mass spectrometry. We looked at ionization, acceleration, and then the magnetic fields deflecting these masses of particles, and then the detector. And then we looked at how to interpret mass spectra. It's really not that complicated because most of the time we're just looking for this parent peak. In this case, it's 100. If we want to, we can look a little bit deeper at some of these fragmentation patterns. Remember, this is the parent peak right here. This is the overall molecule. All these other little peaks right here are fragments of this bigger molecule. We're also assuming that this is a pure compound right here. So this is just one molecule that got broken down into all these little tiny little pieces right here. That's typically what mass spectrometry gives.